So let's go ahead and take a look at the simulation again with our walkers and runners. So we're looking again at a population of 1,000 people, 250 of whom are walkers. So remember, that means that P, our population proportion, is 25%. This time we increase our sample size to 100. So this time N equals 100, and then I just started pulling samples of 100, samples of 100, samples of 100. Did random samples of 100 10,000 times, and I graphed the frequency for the proportion of walkers in each sample. All right, so what do you notice about the shape of the graph? So the first thing I hope that jumps out at you is that this is almost like a normal distribution. It's definitely symmetric. I'd say roughly symmetric, right? It's not skewed, skewed left, skewed right, or anything. It's roughly symmetric, and it actually approaches what will be a normal distribution later on. And what do you notice about the variation? So remember, variation is how horizontally spread out it is compared to the previous graph. So the previous graph, here was what our graph looked like. So there was definitely some gaps in between. This time, there's a smaller variation. So we have less variation. And I would say that the graph has more cluster around this center, right? So if the center's at 25% again, there's more clustered values near that center. Okay, and this is really significant stuff. And the reason that's happening is because we increased our sample size. The larger the sample size, the closer we're going to get to actually a normal distribution, and the less variation we're going to have. And that's really what you ultimately want. You want less variation between your samples. So the estimation remains unbiased. The center, notice, was still at 25%, which is the actual population proportion. The shape of the histogram looks symmetric. We'll say more symmetric. I'm going to abbreviate, more symmetric than the one for sample sizes of 10. The estimator is more precise because it uses a larger sample size. That's really the takeaway. The bigger the sample, the more precision you're going to have. The standard error, remember, is based on the sample size. And so the standard error is going to be smaller than it was with sample sizes of 10. So let's kind of summarize the takeaways here for these simulations. So the estimator P hat is unbiased. So unbiased for all samples. And the key with this is that as long as we take samples randomly, in this case I did because I let StatCrunch, I let the technology do the sampling for me, so I was able to do it randomly using that. So as long as we take a random sample, our P hat is always going to be an unbiased estimator. The precision improves, and what that also means is that the standard error gets smaller as the sample size does what? What do we want? We want the sample size to increase. So as the sample size increases or gets bigger, our precision improves because our standard error gets smaller. The shape of the sampling distribution is also going to be more symmetric as sample size increases. And that's the most important thing here, is that sample size really makes a difference. So again, a little bit of a summary here of what we've been talking about. So finding bias and standard error. The bias of P hat is going to be 0. And when we work with these, we're always going to take a random sample. So our bias, we can say, is always going to be 0 for P hat. The standard error of P hat, now how we can compute the standard error, we're actually going to have a formula for this that you're going to want to know. It's a very easy computation. The standard error, we're going to use the formula. It's the square root of P times 1 minus P divided by N. So remember what those variables stand for. P, remember, is the population proportion, and N is going to be our sample size. Okay, so to compute the standard error, we're going to use that formula if the following conditions are met. So the first condition, the sample has to be done randomly, and they should tell you that in the question, so you don't have to guess or assume. They should mention that. If the sampling is done without replacement, which ours will be, the population must be at least 10 times larger than the sample size. So these are the two things you're going to need to check for when you're working with these problems to compute the standard error. So let's do a quick example here. So it says suppose that in the Matanzas 5K race, there are 1,000 participants and 25% are walkers. So what I would do is I'd start writing down what I know. So from that sentence, I know right off the bat that P is equal to 25%. That's the population proportion of walkers. We are planning a survey in which we take random samples of 100 people. So what does that mean? That means N is 100 without replacement. And notice they said random, so there's that word. We calculate the proportion of people in our sample who are walkers. So part A says, what value should we expect for our sample proportion? All right, so since this was a random sample, so since we were told it was a random sample that we were taking, or we're taking random samples, that means that P hat is unbiased. Okay, so if P hat is unbiased, what does that indicate? That indicates that we expect, so we could also call this the expected value for our sampling distribution. It should be the same as the population proportion, which is 25%. So I expect my samples to get about 25% of my 100 people in each sample to be walkers. Could be more, could be less, because we know it's going to vary from one sample to the next. But we expect our sample to have about 25% walkers because it's an unbiased sample, because it was done randomly. All right, so the next question is, what is the standard error? All right, so to compute the standard error, so to use this formula, these two things have to be taken care of. First of all, the sample has to be done randomly. So let's see, did they tell us it was random? Yes, so the sample was conducted randomly. And then the other condition, so the second condition up here, says that if the sampling is done without replacement, the population must be at least 10 times larger than the sample size. I like to write some notation for these when I'm doing these, so what I'll do is I'll say, okay, what I'm looking for is the population size has to be greater than or equal to 10 times N, which was the sample size. So in this case, the sample size, remember, was 100. So what needs to happen is the population needs to be at least 10 times 100, which it was, remember, because they told us that the population was 1,000. I think they said in the question. Yeah, right here. There are 1,000 participants. So we are good to go on that second condition. Our population is 1,000 exactly. So it's just large enough to work out as 10 times our sample size. So then let's go ahead and compute the standard error. So the standard error, here, let's see, let me write it down here. The standard error, using that formula from above, so the square root formula is what I'm using. It's going to be the square root of P times 1 minus P divided by N. So for my example, that's going to be the square root of 0.25 times 1 minus 0.25, remember P was your population proportion, divided by 100. And if I put that into the calculator, I get about 0.043. And if we write that as a percentage, that would be 4.3%. So what does that mean? That means that from one sample to the next, there's going to be a variation of about 4.3%. So let's kind of write all this together as a statement here for this last part. How do we interpret this? I'm going to erase what I have just because I'm out of space. So let me make some room here. So remember that 4.3% number. That's the number you want to remember. So what can we say? We expect there to be about 25% in each sample, but that's going to fluctuate, remember, from one sample to the next. So let's put all this together. So if we randomly sample 100 people, what do we expect? We expect about 25% of my 100 people in each sample to be walkers. This is going to fluctuate from one sample to the next. So then we'll say give or take, how much? How much is it going to fluctuate? That is your standard error. So it's going to say give or take about 4.3% variation from one sample to the next. So make sure you know that formula. See, one sample to the next. Make sure you know that formula for standard error because we're going to use that a lot for the rest of this chapter and the next one.